through a state diagram. This is the state diagram and these are the different states. So let us just quickly look at this. So state and the description. One is of course closed, that means no connection is active or pending. The other is listening, maybe the server is waiting for an incoming call. SYN received, that somebody has made a request, a connection request has arrived, wait for acknowledgement. SYN sent, the client has started to open a connection, that is from the client side. Established, that means a connection has been established and normal data transfer state, that is the normal data transfer state. Now while finishing, FinWait 1, this is the client has said that it is finished, and FinWait 2, that is the server has agreed to release. So that is the state. And timed wait, wait for pending packets. This is, as I said, the 2MSL wait state. So for the pending last pending packet to come in, you have to wait at least this much. This is the maximum segment life. This is sort of estimated from the round trip time. Closing, both sides have tried to close simultaneously. That is again another. So both sides have sent fin and close wait. Server has initiated a release, and last act waiting for the pending packets. So when it is closed, of course nothing is happening. Now some SYN or SYN plus ACK it receives. So once it receives that, it goes to the SYN received state, and then this way. So as we have explained earlier, this is the connection setup phase, and once the connection is set up, it reaches the established phase, and then the two-way communication is going on. Then after this, it may sort of go through the closure, either through the closing and then FinWait 1, FinWait 2, time wait. So let us not go into the details of this part, and here the close wait and the last act. So this is very roughly the state diagram of TCP. Let us just look now a little bit into the flow control that is implemented by TCP. So this defines the amount of data a source can send before receiving an acknowledgement from the destination. TCP uses a window imposed on the buffer of data to limit the amount of data sent before an acknowledgement must be received. So this is the traditional sliding window protocol, which we had discussed while discussing the data link layer. So we will just go through this very quickly now. So in the sliding window protocol, a sliding window is used to make transmission more efficient, as well as to control the flow of data so that the destination does not become overwhelmed with data. So what is done is that, suppose this is the occupied part of the buffer, and out of this a number of packets or segments have been sent, but they have not been acknowledged, and these are the next byte to be sent. This is what is there in the buffer. Now depending on the window size, now say the buffer contains so much. Now depending on the window size, it can go on sending these bytes, or if the window size is already over, then it has to wait here. So this is sent and acknowledgement, and sent and acknowledged. Suppose nothing has been acknowledged as yet, and let us assume that the size of the window is 3 units. In that case, the sender has to wait here till some acknowledgement comes, and if the acknowledgement comes, suppose 200 is acknowledged, then the window will automatically slide, and this now can be sent. So on the other part also, he is receiving the he has received 194, etc. So these have So these have been received. So this is the occupied part of the buffer, and from this buffer the destination process will keep on consuming the data from these segments as a stream of bytes going out of this segment, and this is the empty part of the buffer where new segments can come in. So suppose the size of the receiver window is this much, let us say size is 7. So after having sent this, the sender can go on sending up to the receiver window size. The point is that if it is if a window size is not fixed, what the sender might do is that the sender may send in a lot of packets, or maybe the channel is absolutely bad. In that case, none of the packets have received on the has gone to the other side, and so you will have to send all these packets once again. That is one point. And secondly, the sender may be very fast, but the network may be congested. So the sender will push in a lot of data, but that will only make the congestion worse, and so whatever would have received on the other side, now that does not reach the other side because the intervening network has been congested, maybe some buffer has overflowed, some router has dropped some packets, etc. So there is a limit on the window size. Of course, the window size also has a bearing on the speed at which effective data transfer is taking place. If the window size is very small, then after sending, suppose the window size is only 2. So after sending 2 segments, the sender has to wait till the acknowledgement comes back. So the efficiency of the channel goes down, because for each acknowledgement, of course, the packet will reach the other side, and then the acknowledgement will travel all the way back. So it is a round trip delay. So suppose the window size is only 1. So after sending each segment or each byte, you wait for the round trip time, and then you send the next byte. So that becomes, now the overhead has become very high. Of course, this is the minimum possible rate at which the sender is sending. On the other hand, if this window is very large, a large amount can be sent even without waiting for acknowledgement, and everything is fine. So the stream of acknowledgements will also come start coming in after this round trip delay, and the overall efficiency would be high. So between the congestion and the efficiency at which data can be transferred, the data transfer speed, the effective data transfer speed, so there is a trade-off. So the details of the sliding window, we have discussed sliding window protocol earlier, so I will not go into the other details of the sliding window. So as the acknowledgements are received, the window slides, and as data is received, now this is the point. Suppose these are the sequence number. Now suppose in the receiver side, maybe say 205 has got dropped somewhere, 206, 207, 208, 209, etc. has come. So after acknowledging 204, where he will, in the acknowledgement packet, he will say that the next byte I am waiting for is 205. Although 206, 7, 8, 9, etc. have been received, but he will not send any acknowledgement. So after some time, the sender will sort of realize that the next this acknowledgement for 205 has not come. So he will start pumping this 205, 6, 7, 8, 9 again. As soon as, suppose, the next 205 actually arrives. So as soon as 205 arrives, what happens is that this gap is closed, and the window will slide all the way here, and he will say that the next byte that is expected is 210. And then what will happen is the 206, 7, 8, 9 now becomes duplicated segments on the receiver side, so they are simply dropped. So using these segment numbers, not only we can put them in order, suppose 206 has come earlier, 205 has come but has come later, but then they can be put in the proper sequence because the sequence number is there. That is one thing. And secondly, even if this 205 was lost, it can still be recovered by this retransmission, etc. So that is how this protocol is reliable. And of course, when this is acknowledged, the window slides. So this is the size of the receiving window. So this way, and what sometimes what happens is that, and we will discuss the details of this later on, if there is actual congestion in the network, that you will find out only after sending some packets and then seeing that some acknowledgements are not coming and the packets have got lost. So what the sender then the conclusion that the sender draws from not receiving acknowledgement, etc. One thing is, of course, this packet may have got lost. That is one thing. And secondly, lost why? Maybe that the network is congested. So what will happen is that there is a mechanism for automatically reducing the window size, so that now you are going to transfer data at a much lower rate, but then you are sort of trying to control the congestion. So this is the congestion control that is inbuilt into TCP. There are some variations as to how this window size is going to be changed over time, etc. So we will come to that later on when we talk in more details about congestion control.